cool rock that I found. It's called obsidian.
Does it have any bubbles in it?
It looks really shiny.
Yes.
Hi everyone.
Oh, look at me. Hi, Bridie. How are you?
I'm pretty down, to be honest. I'm a bit disappointed that we can't do the science festival this year. I was really looking forward to going out and filming some lava and then bringing it back to talk to everyone. We just can't do it this year.
Is that your lava in the background there?
Yeah, it would have been really cool, but we can't travel.
I've had an idea though. We all know lots of really cool things about lava and volcanoes, right?
Yeah.
Yeah.
We do.
Why don't we focus on the things that we can do? We've got lots of rocks and experiments.
What sort of experiments do you think?
I don't know. I've got some experiments. One of the things I would like to do if I had to do it on film is show everyone how we had different ideas about how volcanoes work and how you can make hypotheses and test them, and that sometimes they don't go right.
Oh, you mean like in the past when we were trying to work out what lava is?
Yeah, I think I can show some experiments about that.
And I could get all my rocks out. I've got so many rocks. I've got giant pumice, I've got really cool lavas, I've got a massive obsidian.
Cool.
Wow, Bridie, that's pretty cool. Lots and lots of rocks.
Yeah.
What do they show?
They show how the different rocks that come out of a volcano tell us about what happened when the volcano was erupting, even if we didn't see it.
Oh, and I've got an experiment where people can do at home with a sweetie that shows how lava freezes and gets solid and shows some of those textures.
Cool.
I've got a really fun one that involves honey. Really easy to do at home as well. And all you need is a bit of rice, and you can have a look at how the different textures of the lava when it's been erupted have affected how it flows down slope. So that's really fun.
Oh, that does sound fun.
Cool.
Could have a lava race.
A lava race.
Lava race. Awesome. That sounds great. But your picture, Bridie, reminds me that even when there's lava flows, sometimes volcanoes have explosions. So we shouldn't forget about doing some explosion experiments. You think we should do some of that?
Yeah.
That sounds like fun.
Cool. Well, we've got a series of videos.
It's going to be great.
What is this going to be called, Bridie?
I think Lunchtime Lava.
Lunchtime Lava.
Love it.
Fantastic.
Love it.
Welcome to Lunchtime Lava. So these days we can see lots of amazing footage of lava flows all around the world. But something that we still can't see is inside the earth to see what happens before the lava gets to the surface. And that's been true for a long time. But one of the great things about being a scientist is that when you can't see something, you can wonder about it and make a hypothesis and then do some experiments to see if it's correct. And I'm standing here next to a pretend volcano to show you one of those experiments. Because sometimes you make a hypothesis and actually you prove yourself wrong. And that's okay, because you still learn a lot of things. And I'm going to show you here a very famous experiment done by a very famous chemist, Sir Humphry Davy, a long time ago, over 200 years ago. He discovered the alkali metals, and when he discovered them, he also discovered that they're really quite explodey. So he wondered, I wonder if that's what it is that drives volcanic eruptions. And so he did an experiment to demonstrate what he meant with his fellow scientists with the alkali element potassium. Now that experiment's a little bit too dangerous to do inside, and also a little bit too dangerous for me to do. So that's why I'm standing outside, and that's why I've recruited super top chemist from the University of East Anglia, Stephen Ashworth, who's going to perform this experiment for me in a minute. Take it away, Stephen. pretty convincingly like a volcano, eh? But actually, Humphrey Davy was wrong, and he admitted it later. He went off and did a load of experiments on an actual lava flow on the slopes of Vesuvius in Italy. And he figured that if this was right, he should be able to measure the same kind of gases as this reaction gave off. And he couldn't. And he did all sorts of experiments in the lava flow and eventually concluded that they were not formed by the alkali metals. So another thing it took a long time to figure out is where the magma was coming from and how it got out to the surface to make things like lava flows. So we've got an experiment here that once we get it set up will show us how the people centuries ago started to figure out how this worked. So we've got some of the ingredients that you need. So the wax here is magma. And then we've got some sand that is the layers of the earth. And Ricky's going to pour in some more sand to show that the magma was really quite deep below. So how do you get it up? So once he's got the sand in, then the other thing that we need to have is the place that the magma will erupt into. So it can be a lava flow, or sometimes it can come out a bit more violently. So instead of air for the atmosphere, in this experiment, we're going to use water. So Ricky's going to pour in a layer of water into our experiment. Nice and gently. You can see the water slowly making its way down to the sand, making the sand heavy and wet. And then as he pours more in, you'll see it start to make a nice layer for the atmosphere. There we go. Nice and gently, because we don't want to disrupt the magma. Perfect. So now we've got our little experimental setup, and let's see if we can work out how that magma gets out. But at the moment, it's kind of wrong because the magma is hard and cold. And what we need to do is we need to make it soft and hot. So can you do that for us, Ricky? So what's happening is the heat from the Bunsen burner is heating everything up. It's heating up the sand and the water, but mostly it's heating up the wax. And the wax is more quickly going to become soft, hot, and molten. And when that happens, it's going to show us a little bit what happens when magma starts to become hot and molten. You can hear some noises now and see some bubbles. Something's happening. Something's boiling, and I think it's the wax getting hot and liquid. No volcanoes yet, though. Oh, one at the side. So what the hot liquid has to do is it has to push away the sand in order to get up to the top. Is that starting to happen? I can see it starting to, oh, there we go, eruption! So we can see there's a vent that's opened up and it's pouring out wax from it. It's become a place where it's very easy for the volcano to erupt. And what happens, you can see that magma didn't push things up very much, just a little bit, but actually the layers of a volcano form by having the material come back down again and making the magma. And what they also worked out as well, by looking at ancient rocks where we had some of the stuff that's like the sand, you can see old liquid magma that has subsequently become solid pushing its way through the middle of those layers. And that's how they worked out how magma moves through the underneath surface of the earth. So the final ingredient I want to talk about in terms of getting the magma from underneath to make all these lovely lava flows and explosions we're going to look at is gas. And I've got an experiment here that is going to simulate, again, what's going on underneath the ground. And this is an experiment that you can try for yourself at home because it uses quite a lot of household ingredients. So I've got a clear tube here with some water, and then I'm going to add some ordinary vegetable oil. And this again is making the nice layers of earth that we have. Now that looks quite nice, but what I want is a layer underneath that's magma. And we know magma's not clear, obviously. When it's hot and liquid, it's usually red. So let's add some red food dye. There it goes, down through the oil and into the water. So hopefully that little bubble should explode, and what we'll end up with is a nice layer of red material here. So this is what it's like usually in the earth, where we have nice quiet conditions, a bit of liquid, lots and lots of solid rock sitting on top, which is what our oil represents. But what happens is sometimes there's a pulse of new magma, and the really important thing that's in there is gas. Now, I don't have any gas in my experiment now, but these well-known medicine for when you're feeling a bit ill in the morning, called Alka-Seltzer, they do have gas because that's how they dissolve. So I'm going to add a little bit of gas into this experiment and make my magma layer like it would be when a new pulse has come in, nice and full and rich with gas. And let's see what happens. So the very first thing it's doing is it's helping that nice red liquid dye go through the layer. And you can see what's happening here is we've got bubbles of gas coming out. They're rising up through the oil, and then they're bursting nicely. And then the denser liquid is coming back down. So it's set itself up in quite a nice little calm motion. But you can see it's getting a little bit turbulent around there. So that helps that liquid rise up. And that's what happens during an eruption. So if we have a nice gentle eruption like we have here with things coming out nice and slowly, that's when we can have ourselves a lava flow. So that's quite nice, isn't it? We've got some nice gassy liquid coming up, erupting. And then you can see actually here the stuff, the water, once it gets denser, it's going back down again. So it's quite nice, gentle flow. So that's quite good. So I'm wondering whether you're thinking what I should do right now is maybe add a little bit more gas into the situation, do you think? Well, I'm going to, even though I can't hear what anyone's saying. I'm going to get lots and lots of Alka-Seltzer. So this is the equivalent of adding a lot of hot magma with a lot of gas in it all at the same time. Let's get that tablet too. I'm going to put them all in at once. Down they go into my water, and you're going to see they're going to start degassing a lot more violently. Now this is looking a little bit more like some of the things that we're going to look at later on, which is what happens when magma explodes.
My name is Bridie and I'm a volcanologist here at the University of East Anglia. For those of you who are Star Trek fans, I definitely study volcanoes and not Vulcans. And if you watched the previous video, you will have seen how Humphrey Davy used to investigate lava in lots of weird and wonderful ways. But today in this Lunchtime Lab, I'm going to be showing you how I investigate volcanoes. Now to do that, I have to pretend to be a detective. And you're going to be detectives with me today, and we're going to have a look at all of these rocks here and see how we actually figure out what happened when a volcano erupted if we didn't see it happen. So to do that, I need a few things. I need my notebook, like any good detective, a pen, and also a hand lens. Now, you may not have a hand lens at home, so you can also use a magnifying glass. All right, and you may have been learning about rocks at school with the rock cycle. You'll have heard about sedimentary rocks and metamorphic rocks, but the rocks that we have here are all igneous rocks. Igneous rocks are the ones that have cooled from molten magma and solidified over time, okay? So we specifically here have volcanic rocks. These are rocks that actually came out of a volcano at the surface before they solidified. Other igneous rocks cool down slowly underground over time, and they're a little bit different. But today we're looking at the volcanic rocks because they're the most exciting. So, when we investigate volcanic eruptions and volcanoes, we really want to find out how the volcano is going to erupt. And that's because volcanoes can erupt in loads and loads of different ways. And if we want to make sure that everyone stays safe who lives near the volcano, we need to figure out, is this volcano going to erupt with a big explosion, or is it going to erupt with a lava flow? Now, the best pieces of evidence that we have to figure out the answer to that question are the rocks that that volcano has produced in the past. So when we're looking at rocks, we ask ourselves lots of different questions. The first question we ask ourselves is, what does it look like? We can take a look at the colour. So over here we have some really dark rocks, and on this end we also have a dark rock, and then we also have some paler rocks. Now, the colour can tell us a little bit about what the rock is made out of, which is really important for a volcanic eruption. But the next thing we look at is, does the rock have crystals? So in this rock here, you can see that there are some really huge crystals. If we get our magnifying glass, we can see a little bit more of the detail. Now, these crystals tell a story, and when we look at them under a microscope or we analyze them, we can figure out that story, and that tells us about what's going on deep down inside the volcano. Another thing we can look at is, does the rock have bubbles? Now, you can see in this one here, there are loads and loads of huge bubbles inside this piece of rock. Now, this rock is actually fairly light compared to its size. It's not that difficult to pick up. Whereas a rock that doesn't have bubbles, like this one, is really hard to pick up, okay? This one is much, much denser. And you can investigate this at home with a really cool experiment. All you need is a glass bowl and some water. So we're going to pour some water into this bowl. And we can see how heavy or how dense my rocks are by checking to see whether they float in water. So here we have a rock that's a little bit like this one here. It's much smaller, but it's very dense and it doesn't have any bubbles inside. So I'm going to pop that in the water. It sinks, which is what you would expect a rock to do. Here I have a pale rock and it's filled with lots of tiny holes. Some of them are so tiny that you actually can't see them with the naked eye or even with your magnifying glass. But if I put that in the water, it floats, because this rock is much less dense because it's filled with gassy bubbles. Now, those gassy bubbles are what helps the volcano to erupt with a huge explosion, which is a lot more dangerous than a lava flow. Okay. Now, when we think about lava flows, there are lots of different types of lava flow. We can have a runny lava flow that would have formed something like this. This is a basalt. It's a dark rock, it's very dense, it would sink if we put it in water, even though it's got some bubbles. This has some bubbles, but not as many as our piece of pumice that we just floated in water over here. Now, this would have flowed out of the volcano in runny channels, and it would solidify on the top, and eventually it would get hard, okay? Now, if we look inside the lava, sometimes we see crystals. In here you can see these green crystals. These are called olivine. Now, when you're looking at crystals, it's really important to look very closely and look at the shapes and the colours that you can see, because they will tell you what the crystal actually is, which is really, really important to understand the inside of our volcano. So volcanoes, when they erupt, they can erupt in big explosions, they can erupt lava flows, or you might have seen these beautiful red and orange fire fountains that we get. There's a volcano called Mount Etna and Stromboli in Italy. They both erupt with lots of nice fire fountains that produce these red and orange glowing fountains of lava that explode out of the top, but not as explosive as something that would make a huge pumice bomb like this one, because there isn't quite as much gas and the lava is a little bit runnier, so it's easier for the gas to escape. Now, those kinds of eruptions might produce something like this. Now, it looks a little bit like a chocolate flake bar, but it's actually some basalt lava that was thrown out of a volcano, and because it was molten as it flew through the air, it produced these wonderful textures and shapes. I've got another one here that looks very different, but again, it's the same type of lava, and it got thrown out of a volcano and it cooled through the air, and you can see this twisty aerodynamic shape here. Now, that's something that we would look at in the field and see how far away from the volcano it actually got, because if you are going to be near a volcano when it's erupting, you don't want a volcanic bomb to land on your head. That would be very, very dangerous for that to happen. So that's one of the ways that we investigate what happens with volcanoes. Now, these are volcanic rocks, but you can use the same detective skills when you're looking at any type of rock that you might find at home. So I want you to go and use your volcano detective skills to investigate the rocks that you can find at home and see if you can solve any mysteries of your own.
Hi, I'm James.
And I'm Jade.
We're postgraduate researchers here at UEA, and we're here today to talk to you about lava.
So far during this session, you've learnt about varying types of lava and magma. Lava is extremely dangerous for people who live at the base of a volcano, and the resulting hazard depends on the type of lava that is erupted.
So here today, we're going to look at how differences within the lava affects the way that lava behaves and flows. In science, we have a term for this, it's called rheology. So we're considering the rheology of different lavas and how that affects how they behave. So to do this, we're going to have a lava race.
Before we start this experiment, it's important to say that lava can get extremely hot, sometimes hotter than 1,000 degrees Celsius. So unfortunately today we're not going to be using lava, even as volcano scientists are still dangerous to us. We're going to be using honey and rice, which is going to represent our lava.
Today we're going to be working with two different types of lava. On this side, with the cup of honey only, we're going to be talking about real-world basalt. That's commonly erupted in places like Hawaii, and when it comes out of the ground, you can often see it forming really rapidly flowing rivers of lava. On the other side, with the cup of honey and the cup of rice, we've got a different kind of lava. Lava with lots of crystals in it. So this is an example of andesite. And in both these samples, you can see that there are some crystals that are within the rocks. So what's happened with these is as the magma has come up through the surface of the Earth, it's been slowed down on its way up, it cools down, and as it cools, little crystals start to form. So to look at the differences between the two, I'm going to mix the rice with the honey, and then we'll have a race from here. So now we're done. We have a mixture of rice and honey, which is representing these samples here with crystals in it. And we're ready to go.
Before we start our experiment, we need to come up with a hypothesis. As scientists, we have theories that we want to test, and we develop questions that we want our experiments to answer. So what questions do we want to answer with this experiment? We want to understand how crystal content affects the speed that the lava flows down the volcano. Which do you think will flow faster, the basalt or the andesite, which is the honey and the rice?
So here we are at the summit of Mount Norwich, a notoriously dangerous volcano, and the site of our race. So what we're going to do next is we're going to take our lava samples and we're going to pour them into these drain pipes, and we're going to see who wins. So Jade, when you're ready, 3, 2, 1, go. So who's winning?
I think mine has already reached the bottom.
Oh, well, I lose. That's sad.
So the basalt has reached the bottom first, and this is because it has no crystals in it, so it's able to flow freely down the side of a volcano, where the andesite lava has the rice in it, which makes it slower and unable to move freely down the surface.
So in the real world, as we've said, the basalt forms these rapidly flowing rivers of lava, whereas in contrast, lavas like andesite are often seen forming really looming domes of lava, big piles of lava at the top of the mountain. So this doesn't correctly capture the behaviour of andesite, but it does show you the impact that the crystals have on the way it flows. So why do we care? Why have we just done this experiment to look at how different lavas behave? Well, in the real world, people live near volcanoes and they pose a threat to their life and livelihood. So as scientists, we want to understand how these natural things behave so that if they were to occur in the future, we can keep people safe away from them. So that's been our lava experiment. I hope you enjoyed that, maybe enjoy doing it at home, and we'll see you again.
Hi everyone, my name's Dr. Jess Johnson. I'm a volcanologist in the School of Environmental Sciences at the University of East Anglia. Today, we're going to be talking about the processes that make lava rocks look the way they do after they've been erupted. And we're going to be detectives and use our knowledge to work backwards from looking at a rock to work out what happened during an eruption, even if we weren't there to see it. Now, in previous videos, we've learnt about what makes lava come out of the ground and also how to describe rocks when we see them. We're going to use this knowledge in our experiment today. The important processes that we're going to cover today are making bubbles and also cooling the lava down. So we're going to do this experiment using lava toffee. Now, lava toffee, you may have seen this sweetie before. It's also known as hokey pokey or cinder toffee or honeycomb or even sponge candy. You can do this experiment at home, but make sure you get a grown-up to help you because it can get very hot. First, we need to make our liquid lava. We're starting with 100 grams of caster sugar and 1 tablespoon of golden syrup. We heat it up slowly so that the sugar crystals all melt. Once all of the crystals have melted, we'll carry on heating it until it turns into a honey colour. This is like the magma under the ground at a high temperature and pressure. However, we have seen that gas plays a very important role in making a volcano erupt because gas is less dense than the surrounding rocks and tries to rise above the ground. So we need to add our gas, but with magma, the gas is already dissolved in the liquid and forms bubbles when the pressure is released. This is similar to when you open a fizzy drink after shaking the bottle. We're going to add our gas by using bicarbonate of soda. Its scientific name, sodium bicarbonate, is used when you are baking cakes to make them rise. In that case, it reacts with the acid to release carbon dioxide, which is a gas, and it makes bubbles in the cake. In our case, it's the heat of the sugar syrup that releases the carbon dioxide and makes the bubbles. When you add the sodium bicarbonate, it can bubble up very quickly, so please make sure that you take the pan off the heat first, have a big enough pan, and stir well so that you don't have any sodium bicarbonate left. Otherwise, it will make the finished lava toffee a little bit salty. We're using different amounts of sodium bicarbonate to see what happens when lava has different amounts of gas in it. I'm adding half a teaspoon, Ben is adding 1 teaspoon, Jenni is adding 2 teaspoons, and Ricky is adding 3 teaspoons of sodium bicarbonate. Once the sodium bicarbonate has been added and the mixture is stirred, it needs to be cooled. We are pouring our mixtures into 3 different trays. One will cool here in the lab, we'll put one in a fridge and one in a freezer. This will mean that they cool at different rates. So I've broken open all 12 of our lava toffees, and immediately you can see that there are different distributions and sizes of bubbles. The lava toffee that had the least amount of gas in it has smaller bubbles. When we added a little bit more gas, we have slightly larger bubbles. More gas, even larger bubbles. But interestingly, when we added the most gas, we don't seem to have many bubbles at all. This is because the bubbles got so big so quickly that they couldn't support themselves and the bubbles actually collapsed. So our toffee with the most bicarbonate of soda is actually less bubbly. The other thing you might be able to see is that the bubbles have different distributions. So generally, there are larger bubbles in the middle and smaller bubbles on the outside. This is because the lava toffee cools really quickly on the outside and those small bubbles get frozen in. But the inside of the lava toffee stays warm and sticky for longer and the bubbles have a chance to grow and join together. We call this coalescence. So in our toffee, we can see that our bubbles in the middle are larger than our bubbles on the outside. Where have you seen this before? Look back through the videos and see if you can see any rocks that have a texture like that. But it's not just the bubbles that are affected by the the cooling rate and the amount of gas. The cooling rate also affects the solid in between the bubbles. So one thing that we can see is that the faster the toffee cools, the glassier the toffee actually is. So the material in between the bubbles is kind of glassy. Where have you seen that before? Try and think of a rock that is glassy. So that's if the toffee cooled quickly, but when the toffee cools slowly, you might be able to see that this lava toffee is slightly shiny, slightly sparkly. Don't worry if you can't see it now, but have a look on your own toffee. Now those sparkles are actually crystals, because the slower the toffee cools, the more time the sugar has to lump together and form crystals. Where have you seen this in a rock before? Have a look back through the videos and see if you can see any rocks that have crystals in them. So we have seen how changing conditions can change the textures of our lava toffee, just in the same way that changing conditions in a volcanic eruption can change the way lava rocks look. But we can also be detectives and work backwards. If we have a rock and we can look at the textures within that rock, we can work out what the conditions of an eruption were, even if we weren't there to see it. This is what volcanologists and geologists do. We look at rocks to try and work out the conditions that happened a long time ago. We've also learned the importance of gas and cooling rate in our eruptions and in forming our rocks. Keep watching the videos to see what might happen if there's a lot more gas and if it gets stuck and can't get out in a volcano.
Sorts of volcanic eruptions, there's things other than how much gas is in the magma or how much magma that controls the size of the eruption. And Bridie's got a really fantastic set of experiments to show us the control that is exerted by how wide the top of the volcano is. So we would call that a vent, but actually in Bridie's experiment it's the top of a Coke bottle. So in the first experiment, she's got a really small hole which is just big enough to dangle the Mentos. And again, we're cheating a little bit because what we can't do is bring new coke and magma in. So we're using the Mentos to trigger a degassing reaction. And we're going to do it the same way each time. But what's going to happen is the size of the top or the vent of our volcano is going to go. Let's see what happens with this first one, Bridie. On you go. That is what you call a jet, where the gas and liquid is being shoved through that very tiny hole very quickly. And that sort of jetting happens quite often in volcanoes where the magma comes back together and turns itself into a lava flow. A little bit like we've made that flow of coke on the bench. We're going to have to tidy that up. Okay, and so for the second experiment, all Bridie's going to do is she's going to take the lid off the bottle, and the only difference is just those few millimeters where now our vent is the size of the width of the Coke bottle. On you go, Bridie. Let's see what happens. Same number of Mentos. Quite a big difference in height. So a much bigger difference in height than there is the difference in the width of the top of the vent. Okay, so for this third one, Bridie's really gone too far. She's opened up the whole of the Coke bottle and changed the width by centimetres. Can you think in your heads what you think might happen with this third experiment based on what happened with the first two? Bridie, take it away and let's see if what you're thinking about is the right answer. Hardly impressive at all. That kind of overtopping flowing motion is something we see quite often in lava flow type volcanoes, where the magma just comes out and loses its gas very, very quickly. So full marks to you if you were thinking that as the top of the Coke bottle gets wider, it means that our volcanic explosion gets smaller and smaller. In a little while, we're going to show you a much bigger version of a volcanic explosion experiment. But what I've got here is I've got one that shows you the same things going on, but it's an experiment that you can do at home. What you need is you need a tube of stuff that has maybe been keeping multivitamins, but it has, the key thing is that it has a lid that fits really snugly. If you've got really retro parents, some of them might even have old film canisters, and they do quite well too. You also need Alka-Seltzer and you need water. And you might be asking, what on earth has that got to do with volcanoes? Well, it's kind of being a substitute for some of the ingredients that we need for a volcanic explosion. So for an explosion, we need magma, and we need a lot of gas, and we need a situation with that magma and gas that creates a lot of pressure. And sometimes what that pressure does is it causes it to fail. And that's what we're going to do with our experiment. So we've got the tube here. We're going to add a little bit of water to make that magma. And then what the Alka-Seltzer does is when it hits the water, it creates a lot of gas. So it's a kind of pretend situation we have in a volcanic eruption where lots of magma is losing a lot of gas fast. And what that does is it creates pressure. And we create the pressure here by putting the lid on. Now, when you do this at home, you need to make sure, like me, you're doing it outside because it can make a bit of a mess, and you have to be absolutely sure to step back as soon as you put the lid on, because what happens is that gas builds up the pressure, and sometimes what happens is the pressure gets so big that it causes the lid to fail and pop off, and that generates that explosion. Did you see it had so much energy that basically it threw the lid pretty high up into the air? Hey Martin, what's this?
Hey Jenny, this is what we call a volcanic bomb. You see, volcanoes don't always erupt just lava, but often we have huge amounts of gas in there. And you can see this in here. All these bubbles was gas trapped inside the magma, and it tried to come out. It expanded much quicker than the lava around, and so in the end it all blows up. That's why we get big explosions.
What about this stuff?
Outside you can see it almost looks like a nice fresh baked bread. That's why we call this bread crust bomb.
It's fantastic, and gas is really important. So does that mean that when volcanoes erupt, it's not always lava?
That's exactly right, Jenny, yeah.
Wow, so I've actually got a really good pretend volcanic explosion experiment that we can do. Yeah, so we have to pretend something. So we have a barrel back here, that's going to be the volcano, and then the gas, which is really important, is going to be liquid nitrogen. And what we're going to do is pour the liquid nitrogen into a bottle, and then what's going to happen is there's pressure is going to build because the gas is going to want to expand, and then suddenly that bottle's going to fail. And that's exactly what happens during a volcanic eruption when there's an explosion. Basically there is sudden failure either of the surrounding volcano or the magma. So we're going to be able to see that in something that we call the bin bang.
experiments were really, really fun.
They
but
were.
why?
I learned a lot as well.
Yeah, but why? Why do we do it? Why do we want to do science about volcanoes and lava and stuff?
James, that's a really good question. Actually, volcanoes are all around the world. There's over 1,000 of them that might erupt, and there's hundreds of millions of people who live nearby.
Wow.
So all these things we're learning about can affect people. And by studying the rocks and understanding how they work, one of the things that we can do is make better decisions when a volcano erupts to try and help people get out of the way in time and also to minimize the damage. So it's really important that we do all this kind of learning.
That's great. Yeah.
And I can actually think of a film that everybody loves that has a huge volcano in it and is an excellent example of why we care about volcanoes.
Wow, Bridie, that's excellent. So if you guys have really enjoyed our Lunchtime Lava, why don't you pop along and watch Bridie telling us all about the risks and management of it in The Lord of the Rings.
Bye.
Bye-bye.
Bye. See you soon.